So without much ado, shall we begin the session? The first speaker is Anupreeta More. I hope I've pronounced your name correctly. And the title of the talk is Detection of Gravitational Wave Sources and Gravitational Lensing Effects. So the talk is 45 minutes.
Firstly, I would like to begin with thanking the organizers for the invitation and the kind hospitality. So in today's talk, I'm going to touch upon the main tensions in the standard cosmology and then focus on gravitational waves and lensing of gravitational waves to understand what promise they hold in this context. So as we know that the standard cosmological model, including just a few parameters, has explained a plethora of observations starting from Big Bang nucleosynthesis to cosmic microwave background to abundance of galaxy clusters and so on. There are a few unresolved mysteries, for example, what is the nature of dark matter, dark energy and so on. Nevertheless, we are at a place right now where the observations are getting more and more precise, and we are starting to see some tension. One of the main tensions is this H0 tension. H0 is the Hubble constant, which is the current expansion rate of the universe, and this tension mainly exists from the experiments from the early universe like CMB and the late universe like cosmic distance ladder. So we measure the temperature fluctuations which are imprinted in the cosmic microwave background arising from the density fluctuations underneath. We can measure we can infer these cosmological parameters such as the Hubble constant by fitting a cosmological model to the angular power spectrum, this kind of angular power spectrum. And the latest results from the Planck collaboration, they predict a value of 67.4 with a sub% accuracy on the H0. Contrary to this, from the late universe, we have the distance ladder comprising Cepheids and Supernovae. These are both standardizable candles, and the period luminosity of these Cepheids, this has been calibrated using geometric distance measurements, and these Cepheids are then used for calibrating the supernova intrinsic brightness, and this is how we build this cosmic distance ladder to then directly measure the Hubble constant. And here are the latest measurements from the SHOES collaboration. The value is 73.2, and so there are a bunch of different late universe probes, but I want to talk about just one more late universe probe, which is a completely independent way and a single step measurement of the Hubble constant, and this is based on gravitational lensing. So we expect that a distant source which is well aligned with a massive galaxy in the foreground will show multiple images of this background source, and if the sources are transient and they're variable, then we can see the time delay between these multiple images, because these different images they cover different geometrical paths and experience different gravitational potential. In 1964, Refsdal first pointed out that if we can measure the time delays between these multiple images and characterize the lens potential along with the information about the distances to these objects, we can then get a measurement of the Hubble constant. So even though Refsdal had lensed supernovae in mind, as luck would have it, there were a lot of lensed quasars that were available, which also show intrinsic variability, and these are good probes for the time delay based cosmology. And so there has been a few collaborations like the Holy Cow collaborations and the TD Cosmo collaboration. They have religiously studied a handful of these lensed quasars by conducting a long time scale monitoring of these lensed quasars to measure this variability and get a Hubble constant measurement to a few percent precision. And this initial results from the Holy Cow collaboration, they point to a phi sigma tension with the early universe probe. If these models are also including some of the degeneracies, for example the so-called mass sheet degeneracy, then the measurement of these Hubble constants and the error bars, they are much more relaxed, and then they come into the agreement with the various probes, the late universe and the early universe probes. So the great thing about the analysis, the way the analysis is done by these collaborations is that they have tried to do a blind analysis, and this minimizes the confirmation bias, and I think it is a great way one should go about doing these kind of cosmological inferences. So other cosmological probes should also try to include these kind of blind analysis in their approach. One of the disadvantages of using lensed quasars, as far as I know, is the tedious monitoring one has to do over decades, and this is a really painstaking business. So we do need better probes for sure. Of course, in the recent times we have started to find lensed supernovae, and so using time delays of lensed supernovae is going to become a reality very soon. The lensed supernovae are somewhat a better option. One of the reasons being that if you have lensed supernovae of type 1a, then these are standard candles, and these allow additional constraints that are not possible from lensed quasars. There is also the fact that these supernovae are transient, and so after a period of time the supernovae will fade away, and you will be able to get much clearer picture of the host galaxy, the lensed host galaxy, which you can then model much more accurately, which is not possible for lensed quasars. There are of course some complications. For example, we tend to find these microlensing effects which arise from the perturbations which are perturbations due to the stars or the stellar population located in the foreground lensing galaxy, which happen to lie close to these multiple images of the lensed source, and they cause fluctuations in the fluxes of these lensed supernovae here. So as a result, the light curves have fluctuations which are also time dependent, and these fluctuations are different for the different lensed images, because the stellar population that is in the vicinity of these individual lensed images happens to be different. And so this microlensing introduces much more complexity and makes it difficult to use lensed supernovae for these time delay based cosmology. Of course, if you also have these lensed supernovae which are lensed by a more massive galaxy cluster rather than individual galaxies, then they are less affected by these microlensing effects, but the mass distribution tends to be much more complex in galaxy clusters, which again makes it less appealing. Anyhow, in summary, we can see that there is a tension in H0. Here is a plot from Di Valentino et al. Which points out how the early universe measurements look like versus the late universe measurements, and you can see this tension. We don't really necessarily understand the origin of this tension, or whether it truly points to hint of new physics. There are also possible resolutions, and I'm sure you're going to hear more about this in the plenary talk by Eleonora herself, I think tomorrow. So let me move on to gravitational waves, which is another interesting upcoming late universe probe. So Einstein's predicted gravitational waves, existence of gravitational waves, and in the last few years with observatories like LIGO, Virgo across the world, we made a first direct detection of binary black hole system, and so far all the gravitational wave sources that we have discovered until now, these have been from the inspirals of compact binary coalescence. So these compact binary coalescence CBCs, they are merging binaries comprising of pair of neutron stars or a pair of black holes or a neutron star and a black hole, and with general relativity we can predict how these gravitational wave signals look like. These pair of objects, they emit gravitational waves as they come closer and closer, and the orbit decays, resulting in a merger followed by a ring down of the final black hole. These signals, since they are well defined, the theory behind this is well defined, we can understand them based on the various intrinsic and extrinsic parameters, for example the masses and the spins of the binaries, and the distance or the sky location, inclination, and so on. So here is a pictorial representation of the latest results from the LIGO-Virgo-Kagra collaboration, showing various binary black holes, binary neutron stars, and so on that have been detected. So, so what are the things that one can do with these gravitational wave signals detected from the CBC sources? So one of the things is people have proposed that these the CBC signals, they can act as standard sirens, because we can measure the luminosity distance directly from the shape and the amplitude of the gravitational wave signal, and if we have an electromagnetic counterpart to such a binary, then we can get an independent redshift measurement from the EM counterpart by identifying the host galaxy, and with this we can construct the Hubble diagram and get a constraint on the Hubble constant. And this was very well shown by the first binary neutron star GW17017. So here's a plot from that LIGO collaboration paper showing the H0 measurement with this solid curve, and these vertical shaded regions are again results from Planck and the Schulz collaboration for reference, and you can see that these measurements are in agreement with the previous constraints. There are also other ideas where if the gravitational wave signals do not have an EM counterpart, we can still use them as dark sirens. There are different approaches people have taken, and many of the references are listed below, but I'll just mention one of the first papers which highlighted this idea. In this case, if you don't really have a direct EM counterpart, then one can still try to obtain redshift information by looking at all the galaxies that are there within the sky localization of a given event, and then do the same analysis for many more events, and thereby statistically get constraints on the Hubble constant. Again, one can refer to many other ideas that are developed in the literature, but I would like to just show this one result from the LIGO collaboration, which takes into account the latest set of gravitational wave events. And here what we can see is in these orange dashed curve are the constraints from 47 gravitational wave events, whereas the black one shows the single binary neutron star event, and then in the combined result is shown here in blue. Again, for reference, there we can see the vertical shaded regions showing the Planck and Schulz results. So I want to briefly talk about how challenging the detection of these CBC sources itself is. For an example, here is a CBC signal embedded in the noise, and you can see that how weak this signal is. So there have been many approaches, many methods that have been successfully implemented, but still many challenges remain. So one of the standard methods that people use is called the match filtering method, and in this the idea is to take a template waveform and then cross correlate with a data segment. The match filtering, this gives you the strength of this correlation, and one can then apply some sort of thresholds on how strong the correlation is and how well the match is between a signal and the template waveform to then decide that there is a signal present in the data. I have added some reference for some other searches that have been again used successfully, but I would like to quickly mention some of the upcoming methods that involve machine learning. So, for example, there is this project called Gravity Spy. This includes machine learning combined with citizen science as a means of identifying different noise sources, noise features that are there in the data, characterizing them and understanding their origin, and so on. There is also a study by Jadhav et al. 2020 in which again machine learning framework is used to further improve the significance of the events that are found from the match filtering step and reduce the background that is there in the data. The reason why I am trying to highlight the machine learning approaches is because as we move towards better sensitivity with the detectors, and we are hoping to find a lot more signals, we are going to receive a lot more data, and it is really important to have faster methods which are also efficient in finding these signals so that we can rapidly find these signals, and in some cases where we do need to find the EM counterpart, we can rapidly then trigger those multi-messenger kind of analysis and so on. So searching for these signals is like searching for needles in a haystack. Apart from just the background, the Gaussian like noise that is there in the data, there are also other transient noises called glitches, and here are some examples shown of various glitches in the frequency versus time domain. So there are many of these glitches. One of them is this blip glitch, which has a similar morphology to a gravitational wave signal, and this the occurrence of the blip glitch is very high in the data, and it has been extremely difficult to distinguish these blip glitches from the CBC signals. Here is another figure that shows in time series format how the blip glitch shown in blue looks, how similar it looks to a template waveform which is overlaid. And so there are many machine learning methods that people have tried to develop to distinguish these binary black hole signals from blip glitches in particular, but I would like to just talk about one particular study here where we are trying to use a different data representation compared to what is normally used, which are either time series data or time frequency spectrograms. So here what we are trying to do is we cross correlate the signal with a sine Gaussian function and project those correlations in the parameters of the sine Gaussian functions themselves. So the x and the y axis here, these correspond to the parameters of the sine Gaussian function, and you can see that for a simulated binary black hole signal, the projections appear in certain regions of this parameter space. Whereas a blip glitch looks something like this, and a noise only data has basically this kind of projection. And so we have made use of this sine Gaussian projection maps, developed a neural network to then distinguish these binary black hole signals from the blip glitches, which are more of a challenge at the more massive end. And so in this plot we are showing the receiver operating characteristic curves, where for different SNRs we have shown how well our method works compared to some of the other methods that are there in the literature. And we have also then tested our network on real sample of gravitational wave events from the latest catalog, and we find that 95% of the events are correctly identified. Of course, this is a first limited analysis that we have done only with blip glitches, and in the future we are planning to expand it to other glitch categories so that we can use this method for distinguishing the binary black holes from the broader classes of glitches rather than just the blip glitch. Okay, so now I would like to move on to the gravitational lensing of gravitational waves. So just like the lensing of EM sources, we do expect the gravitational waves also to be lensed, and since in gravitational waves we are mainly looking at time domain data, the main lensing observables, if we are going to see lensing of gravitational waves, is that we are going to see events arriving at different times, and because of the lensing magnification, which will be different for these events, they will seem to arise from different luminosity distances. We also expect phase shifts between the different types of images, and of course given the relatively poor sky localization, which currently spans about 100 square degree or so in the sky, we expect these multiple events which are lensed, we expect them to arise from the same direction in the sky. Of course the physical parameters like the masses and so on are also expected to be the same. So in order to motivate the kind of science that we want to do with lensing of gravitational waves, we also want to understand what are the lensing rates, how often do we expect to see lensing in the current detectors or in the future detectors. And so there have been multiple studies which have tried to calculate the lensing rates for binary black holes, binary neutron stars and so on. So here I have listed one such table. Here this includes different models for the merger rate densities of these binary sources, because right now there is quite a bit of uncertainty in the knowledge of these merger rate density models. So we have explored different models and predicted what the lensing rates are going to be like. Let's say in some of the best cases, we expect about 1 in 1,000 events to be lensed by galaxies, and also there are going to be galaxy cluster, much more massive systems which can also act as lenses, and these are also, they also have roughly similar rate, but they are somewhat rarer than lensing by individual galaxies. As I mentioned that there is all this uncertainty in the merger rate density model, so we can turn this problem around and we can say based on the detection or non-detection of any lensed events found in the data, what can we learn about these merger rate density models, or how well we can constrain. So this is roughly depicted in this illustrative plot. So I would like to just again, there are many methods, there are many algorithms people have developed for finding lensed events in the gravitational wave data, but I would like to just mention a couple of them which are rapid means of identifying strongly lensed candidates. So one of them is this work by Harris et al. 2018, in which the main thing that they are proposing is that given given the given a pair of events which are going to be strongly lensed, some of their parameters will be similar, and so if you are looking at the posterior distribution of these parameters, then we expect them to have overlap for a true pair of lensed events, and this is captured in this B overlap factor. They also have come up with this RGAL factor, which relies on the fact that the time delay distributions for a population of pair of lensed events is going to be different from a random population of pair of events, and so they propose this method to they propose this method in which you combine the B overlap and RGAL to then identify candidates which are most likely going to be strongly lensed, and these kind of analysis done on mock samples to show how efficient these methods are going to be. Another approach that I wanted to mention is based on machine learning. This is again very important to have something that can rapidly discover candidate strongly lens systems, so that it is possible to do subsequent analysis, much more detailed analysis, or any other follow-up that one wants to do. And so in this work, they are again relying on the fact that true lensed events will have overlap in the sky, and they are making use of the time frequency spectrograms and looking for similarities in this kind of maps for the lensed event pairs, and they're using this to distinguish unlensed event pairs from the lensed event pairs. And again here the performance of their network is shown in comparison with previous studies, and they seem to show comparable results. I would also like to just bring up another recently done work in the same direction, which is improving upon the RGAL that was proposed in the Harris et al. So what we are proposing is a modified version of this RGAL, so we call it MGAL, here where we are saying that instead of only using the time delays, we can also use other lensing observables that are there, because they are all these lensing observables, they are correlated with each other. And so if we make use of these jointly all these lensing observables, then this new statistics will provide an improvement in the efficiency with which we can find these strongly lensed candidates. And so here, for example, here is the B overlap versus RGAL shown for a pair of promising events from the LIGO collaboration, if something is if a pair of event is a genuinely lensed event, then it's supposed to have a high value both for the B overlap and RGAL. So with our analysis, what we are showing here is that when you use this joint information, then you can increase the ranking, the rank that you assign to these pair of candidates. So that is shown here for with a pair of events. So the one that is highlighted in the red, this particular event, we can boost the value of the rank that is assigned to this if we make use of MGAL. So here you can see this green contours show the lens population pair of events, and this particular pair of event lies very close to the peak of the lens population. And so if we replace this RGAL by MGAL, then it boosts the ranking statistic for this particular event pair, and it pushes it towards the right hand side. Although in this particular case we are not really claiming any particular discovery, it's just that we are demonstrating that one can get improvement if we make use of these joint observables. along the same lines, there is another analysis where we have tried to understand what is the impact of making assumptions about certain lens models which allow us to get these joint observables. So because there has been some criticism or some reluctance to assume certain lens models because they might bias what those joint observables will look like. So this particular study shows that if we are making assumption for some lens model, it still helps us to better discriminate between the unlensed and the lensed population, rather than not assuming any model at all. And that is shown by these the blue curves versus the red curves in the data. So the blue curves do not assume anything about any of these lensing observables, and the dashed lines here correspond to the lensed population, and the solid line corresponds to the unlensed population. And you can see that there is quite a bit overlap between these two populations when we look at the blue curves. But now if you look at the red curves, the lensed versus the unlensed population, you can see that this confusion is reduced. Because we are making these use of these joint observables. All right, so one of the interesting science that we can do with the lensing of gravitational waves is cosmology, very similar to what I showed for lensing of EM sources. So there was this paper by Kai Liao in which they showed that if you have a sample of lensed gravitational waves where you have also identified their EM counterparts, then the constraints that one can get from such systems is going to be much better even at the sub-percent level compared to a few percent precision that is possible with time delays of lens quasars, for example. And this is one of the main reasons being that with lens gravitational waves you are going to get extremely precise time delays, and one doesn't need to do a very tedious long-term monitoring of the data and so on. And of course gravitational waves themselves, they are like standard they are standard sirens, so those bring additional constraints in your lens models. And so overall this is very promising. The disadvantage or the complications here are that we need to efficiently be able to find the counterparts of these of the lensed events within the gravitational wave data itself, which is a big challenge, and also able to identify their EM counterparts from any of the EM observations. So these are the main challenges if you want to use lensing of gravitational wave, but the returns are going to be way better. So again, to motivate, suppose we are considering systems like lensed binary neutron stars where we do expect to see some EM counterpart. What does the landscape look like for this? So the lensed BNS rates right now are very small, but in the next few years with the design sensitivity of the LIGO and then with the future generation detectors, we expect handful to order 10 kind of lensed BNS events. We have also predicted the time delay distributions in these various detector sensitivity scenarios. This is very important because we need to understand or we need to be able to predict how soon or when the subsequent images, the lensed images, subsequent lensed images are going to arrive. This again is very important because we can then rapidly make predictions for what to expect in the EM data as the EM follow-up is happening. There are also other studies which have tried to assess how feasible it is to detect the lensed counterparts in the EM data, for example using surveys like LSST, which is an optical survey where they are going to go to very large areas and very high depths. So here there is some uncertainty in our understanding of the EM counterparts of this BNS. So these authors have explored different models and considered different lensing magnification factors, but roughly what they find is that if we catch the lensed EM counterpart in the first few days, there is a good chance that we will be able to detect the lensed EM source, which is within the reach of LSST like survey. So this top bar is for the shortest observations that LSST survey will do, and the subsequent bars which go much deeper to fainter magnitudes. These are with multiple exposures taken over the years and so on. Of course, just like we had the standard sirens versus the dark sirens, thanks. Here also people have looked into the possibilities of identifying the EM host galaxies, even if we don't have the direct EM counterpart for the lensed GW source, and people have tried to assess how well we can localize and how well we can identify the EM host galaxies. So there are many studies, and some of them are listed here. So I just want to point out this one study where they have shown that if you have 1 square degree of localization area, then with a Euclid space mission kind of imaging that one will get, it will be possible to identify the EM counterpart about 15 to 35% of the times. There are other studies where there is absolutely no information being used about the EM counterparts, but here these authors are proposing that we can use the abundance of these lensed gravitational wave events combined with the time delay distributions to get constraints on the cosmological parameters. So this is this work is by Jana et al. 2022, and I think you will be able to hear more about this in Souvik Jana's talk in one of the parallel sessions. So I want to talk about microlensing for a bit, because as I mentioned, for lens supernovae, this is much more of a problem, and I'm talking about the microlensing effect arising from compact population which is located in the foreground lensing galaxies like stars, which happen to be close to these images. So from this study of lens supernovae, it has been identified that the probability for microlensing to occur is very high, and we expect to see moderate to significant deviations in the magnitude or in the fluxes of these lens supernovae. Similarly, other studies have identified whether the small image separation or the wider image separations which are going to be more affected, or which systems are going to be much more efficient, and so on. And so when we talk about gravitational waves, then the microlensing in gravitational waves is also something that we wanted to understand and characterize how important this is going to be. So the one difference when we talk about microlensing in gravitational waves is that when you're discussing about strong lensing effects, then we expect the lensing magnification just to be a single factor, and so one gravitational wave signal will just be a shifted version of the other signal. But when we talk about the microlensing effects arising from these smaller low mass population like stars and stellar remnants, then we have to take into account wave optics effects, where we have to calculate the diffraction and interference effects, and in this case the magnification factor is no longer just a constant factor, but it has frequency dependence, and this introduces modulations in the shapes of the gravitational wave signal itself. So we have tried to characterize this microlensing effects. So for example, you have these multiple images, and as I was mentioning that the regions or the vicinities around these images, they tend to show, they tend to lie in different stellar density environments, they correspond to different lensing magnifications. So the effect that will be seen in these individual lensed images is going to be different. And so in this work, Mishra et al. Work, we have tried to quantify which are the dominant effects, and sorry, we find that the lensing magnification is the most important, the strong lensing magnification is the most important effect, and that really boosts the amplitude of the microlensing distortions that we will see in the data. And you can hear more about the microlensing analysis and any other biases and in the parameter estimation and so on in Anuj Mishra's talk, which will be in one of the parallel sessions. We have also tried to quantify the probability of seeing microlensing in the gravitational wave data, and to keep it short, we have only focused in the low to moderate magnification region, specifically strong lensing magnification less than 10, and then we have generated lots of mock realizations of these microlensing effects that we expect to see, and we look at how what is the match between microlensed signal versus an unlensed signal as a function of the total mass of the binary, as a function of the mass ratio of the binary, and so on. Overall, we find when the strong lensing magnification is less than 10, then in most cases we don't see strong effects, and the detection or any other biases in the parameter estimations are going to be minimal. And the question is, what fraction of the lens gravitational waves will have will fall in this parameter space, and the answer is roughly 50% for the upcoming observing runs. And so this also means that the other 50% are likely to show moderate to high effects. And not to mention that with future detectors, these fractions of strong microlensing effects are going to be fewer, but there is also this detection bias that if there are strong effects, strong microlensing effects, strong magnifications, then we are likely to find these events before. So anyhow, we are working on understanding these effects in the more high magnification regime to better understand what sort of effects we are going to see. And at this point, I would like to just end with this summary slide here. Just very briefly, I would like to flash that this talk is not on behalf of the LSC, and I'll just leave with the summary slide up here. Thank you.
We have a few minutes for questions.
Very nice talk, Anupreeta. I have a couple of questions. The first is a naive one about gravitational lensing of gravitational waves. Is it possible that gravitational waves will actually, because of the nonlinear coupling that exists in Einstein's theory, will actually induce extra gravitational waves from the lensing source, like a black hole, for instance. If you take the central black hole of a galaxy, then is it possible that there'll be an induced gravitational wave, which will be different from what how EM signals are strongly gravitationally lensed? So is there a difference between EM lensing and gravitational wave lensing?
So that is a very interesting question. I haven't really thought about this very well. People have considered just point mass lenses for black holes, and as far as I know, we have not really found any additional effects assuming a point mass lens. But yeah, it's something to think about.
Okay. Just one more question, and that's you talked about the CBC at the beginning of your talk. Now there, of course, we have a lot of orbital angular momentum, And usually that is not kept track of in either LIGO, Virgo, Kagra. Are people thinking about how to actually measure the angular momentum? Because most of it will have to be carried by the gravitational waves themselves.
So, can you explain a bit more, like in what context?
Oh yeah. If you have two compact objects going around each other, there's a lot of orbital angular momentum. And when they merge together, usually the spin's low. So there's a lot of additional angular momentum which has to be carried by the gravitational waves. Now, how do we measure that?
So I think this question would be better answered by someone who is more of a gravitational wave expert.
Okay.
I think,
Sorry.
but I think when we have much more sensitivity, then I think it will be possible to look at these more subtle effects, more higher order effects. They might be possible to detect in the data.
There's a couple more questions. I hope the organizers are going to be flexible about this.
Hello, yeah. So basically, just to answer, So basically, currently the way we are probing things is based on waveform models. And the waveform models currently carry information about the spins and basically spin orbit coupling. And that is captured in terms of some kind of a phasing in the inspiral phase. But I think what you're talking about is maybe when it emits, right? Yeah, so I think that is something which people are thinking about, okay, because currently we get information from this waveform model, and if you have some significant signal to noise ratio in the ring down. So the ring down carries that information, yes. So that is something which we are not really able to probe ring down that well because we don't have good number of cycles, but this is something which is being explored. I had one question. May I? Sumit, I had one question.
I think we don't have much time. If we can eat less, spend less time on food, but then I'll be asking too much of the LOC and the participants. I mean, this is food for thought, so this is great. So I'm all for this, but I think I shouldn't overstep my bounds. So there's one question there. So one there, but we will just wrap it up. Sorry.
May I ask?
Yeah. Please go ahead.
So I wanted to ask a question related to supernova rate. So the supernova rate predicted from the star formation rate and the observed supernova rate, till z is equal to 1, let's say, they have a certain level of disagreements. So are these gravitational wave detectors are also measuring the supernova rate, like trying to put constraint on, and like what are the future prospects of measuring the supernova rate with gravitational wave detectors?
Sorry, do you mean the kilonovae rates or?
No, the kilonovae one, the supernova rate.
From the gravitational wave data?
Yeah, is it possible to measure the supernova rate from using the gravitational wave detectors? So
I don't think we can measure the supernova rates with the gravitational wave data. We can look at the binary mergers rates themselves and maybe try to infer something from that, but not directly about the supernovae rates.
Okay. Is this because these detectors are not?
I think so. Just sort of respecting the local organizers and their sort of very strict timing, we can take this outside and please continue the discussion. I also have questions, but I shan't abuse my authority here. So thank you very much for a very interesting talk. And our next speaker is Prayush Kumar about the